Welcome to the first video in our Exploring Science and Technology series. Today, we're diving into the fascinating world of quantum computing, a technology that sounds like science fiction, but is quickly becoming reality. This video will break down complex quantum concepts into simple, everyday terms that anyone can understand. Before we start the video, please subscribe to the channel and like the video. Imagine you're trying to find your way through a maze. A classical computer, like your laptop or smartphone, would try one path at a time, checking each route sequentially until finding the exit. But what if you could explore all possible paths simultaneously? That's the kind of power quantum computers promise. Traditional computers use bits as their basic unit of information. Each bit can be either 0 or 1, like a light switch that's either off or on. Everything your computer does, from displaying this video to sending emails, comes down to manipulating these binary bits. Quantum computers, however, operate on entirely different principles borrowed from quantum physics, the science of very tiny things like atoms and particles. Instead of using ordinary bits, quantum computers use something called quantum bits, or qubits for short. Here's where things get interesting, and a bit weird. While a classical bit must be either 0 or 1, a qubit can exist as both 0 and 1 at the same time. This strange property is called superposition. Think of it like a coin. A regular bit is like a coin that's either heads or tails, but a qubit is like a coin that's spinning. While it's spinning, it's in a sense both heads and tails simultaneously. Let me explain this with a simple example. Imagine you're planning a trip and need to divide 3 friends, Alice, Bob, and Charlie, between 2 taxis. With classical bits, you'd represent each person with a bit. 0 means first taxi, and 1 means second taxi. You'd need to check each possible arrangement one by one, but with qubits and superposition, it's as if you're considering all possible taxi arrangements simultaneously. It's not just faster, it's fundamentally different. Just as classical computers use logic gates like AND, OR, and NOT to manipulate bits, quantum computers use quantum gates to manipulate qubits. These quantum gates are mathematical operations that change the state of qubits. Think of them as instructions telling the qubits how to behave. A simple quantum gate is the NOT gate, also called an X gate, which flips a qubit's state, turning 0 to 1 and 1 to 0. But because of superposition, this gets more interesting. If a qubit is in superposition, the NOT gate flips both possible states at once. Another important gate is the Hadamard gate, which actually creates superposition. It takes a qubit that's definitely 0 or definitely 1 and puts it into a state where it's both simultaneously. Now let's talk about another quantum phenomenon that Einstein called spooky action at a distance, quantum entanglement. When 2 qubits become entangled, they form a connection so strong that whatever happens to one instantly affects the other, no matter how far apart they are. It's like having 2 magical coins that always show opposite faces when flipped, even if one coin is on Earth and the other is on the moon. Imagine 2 friends who somehow always know what the other is thinking. If one decides to wear a red shirt, the other instantly knows to wear a blue shirt, without any communication between them. That's similar to how entanglement works, and it's a crucial resource for quantum computing. When we entangle qubits, we create powerful connections that allow quantum computers to process complex problems in ways that classical computers simply cannot. Now, why should you care about quantum computing? One major reason is cybersecurity. Most of our secure internet communications, from online banking to private messages, rely on encryption techniques that are extremely difficult for classical computers to break. These techniques often use very large numbers that are hard to factor break down into their prime components. For a classical computer, finding the prime factors of a 300-digit number could take longer than the age of the universe. But a powerful enough quantum computer using an algorithm called Shor's algorithm could potentially do it in hours or even minutes. This means that encryption systems we currently rely on could be vulnerable once large-scale quantum computers become available. It's like suddenly discovering that the locks on all the world's secure vaults can be easily picked with a new tool. Fortunately, researchers are already developing quantum-resistant encryption methods that even quantum computers won't be able to crack. It's not all doom and gloom, though. Quantum computers promise incredible benefits across many fields. Drug discovery and materials science. Quantum computers could simulate molecular interactions with unprecedented accuracy, potentially revolutionizing drug discovery. Similarly, we could discover new materials with amazing properties, superconductors that work at room temperature, more efficient solar panels, or stronger and lighter building materials. Optimization problems. Many real-world problems involve finding the best solution among countless possibilities, like finding the optimal route for delivery trucks or determining the best investment strategy. Artificial intelligence. Quantum computing could supercharge AI by allowing certain machine learning algorithms to run much faster and work with larger datasets. This could lead to breakthroughs in pattern recognition, natural language processing, and other AI applications. Where do we stand today with quantum computing? The technology is still in its early stages. Current quantum computers have relatively few qubits, typically under 200, and suffer from errors caused by noise and other factors. Companies like IBM, Google, and Microsoft are racing to build more powerful quantum computers. IBM even allows anyone to experiment with their quantum computers through the cloud, so you can actually write programs for a real quantum computer and run them remotely. Programming a quantum computer is different from programming a classical one. Languages and tools like Qiskit, developed by IBM, allow developers to design quantum circuits, sequences of quantum gates applied to qubits. Quantum computing isn't going to replace your laptop or smartphone anytime soon. Classical computers will still be better for everyday tasks like browsing the web or writing documents. Instead, quantum computers will likely be used as specialized tools for solving particular kinds of problems, similar to how we use graphics processing units or GPUs today for specific tasks like rendering video games or training AI models. The next decade will be crucial for quantum computing. We'll see more powerful machines with more qubits and fewer errors, and as the technology matures, we'll discover new applications we haven't even thought of yet. Quantum computing represents one of the most profound shifts in computing since the invention of the digital computer itself. By harnessing the strange properties of quantum physics, superposition and entanglement, we're opening doors to computational possibilities that were previously unimaginable. Thank you for watching this first video in our Exploring Science and Technology series. If you found this interesting, please like, subscribe, and share with friends who might enjoy learning about cutting-edge technology. Let me know in the comments what topics you'd like to see covered in future videos.